N-type MOSFET has been studied at length. So it has three regions of operations, and there are equations that work in those regions. So generally, if you look at situation, we have to identify what is the overdrive voltage, and especially with respect to the drain source voltage. And with that respect, then we'll know which relationship to use, and that would define how we would proceed in identifying different parameters. So we know we may be given the process parameters like mobility, electron mobility times uh, oxide capacitance, which we identified that to be a parameter of fabrication, and this with W over L, we call it MOSFET transconductance parameter. We can calculate, or this may be given to us. And then we have overdrive voltage. This is a relation which we'll see today because it involves the channel length modulation. Now, when you make a circuit, we use it as three terminal device. It is four terminal because we are also biasing the body, but we write it in terms of three terminals. This is the symbol for the N channel enhancement type MOSFET. So this space between these two specify the difference between the space between the gate insulator and between the gate electrode and the body, which is because of the insulator that's sandwiched between those two. And the arrow shows that from body to the N channel there is a PN junction, and hence there's an N channel MOSFET. It's a symmetrical device, but we use it in circuit in one way where we keep the we don't have to write source and drain, but the way we put it there, it tells us which is source and which is drain. So we put the arrow on the source terminal, so this distinguish for our application that which one is source and which one is drain. Now, these symbols help us see what kind of transistor we are using, and this would readily tell us if the arrow is going out or arrow is going towards the transistor from source. So again, three regions of operation. These three regions are important from us because this will help us identify the dependence of drain current with respect to drain source voltage and as well as the gate voltage. And in that case, then we will relate the gate to source voltage, VGS, because that's the source is on ground. So we would then take the difference between gate and source to see what is the biasing and how does the current change with that. So three regions, three areas of operation. Now these three regions, one is cutoff, right? So where you have no current flowing. So that's when the gate voltage is less than the threshold voltage. So we haven't even turned it on. And the other is where we have small VDS less than overdrive voltage, and then we go equal or above the overdrive voltage. Now the first two regions, the cutoff and the triode region, these are useful when we use it as a switch, which would make it 0 and 1, on or off. But if this MOSFET is used as an amplifier, then we use it in the saturation region. So now this picture is showing it from that physical representation, now we are writing is at a circuit. So this circuit with an NMOS transistor and then two DC supplies with both of them, each one of the one is providing gate voltage, the other is providing drain to source voltage. And we are measuring the corresponding drain current. So if you look at it, so this makes our circuit analysis straightforward. And this can be used to measure the drain current versus drain voltage curves for this transistor. So for each curve, we can set VGS to a desired constant value and just change the drain to source voltage, and that would give us the curve that would be with respect to that gate voltage. Now these characteristics curves are shown, and one is for this region and one is for this region. And we know the pinch off. That pinch off is achieved when VD goes much higher than the overdrive voltage, and then we can see that when that happens, it will not allow the drain voltage to fall below the gate voltage by more than the threshold voltage, and that is what is shown in this picture, that this would not let it fall below the value of the drain voltage. So at any given time, the voltage after pinch off, VD stays higher, so this does not allow VD to go below VG by this factor. This figure tells us what would happen by selecting specific overdrive voltages and how would our curve change. So you can see that by adjusting the overdrive voltage, we can adjust the saturation current. So this means that for whatever drain voltage is, our gate voltage would have an impact on what current do we get for any given VDS. So if you follow this red line, so if VDS is some certain value, so for that each VDS, we can have higher drain current by adjusting our overdrive voltage. So this is an important figure. We would have to remember this, because here the boundary is also important for each plot, the boundary between the triode region and the saturation region, which depicts the parabolic region, and then at saturation it turns into a constant voltage. Now we use this then as a large signal model in saturation when we have cranked it all the way up, and what we are getting is a voltage controlled current source, because now by controlling the overdrive voltage, we can control the saturation current. We can control what level do we get on the drain. So hence this is what you can call as large signal equivalent circuit of a voltage controlled current source. The current here we are taking it in an ideal condition, and now there is one thing important here to note, that we are considering an infinite output resistance. The reason is that small change in drain, for example, if we go from here to here, there is a delta change in drain voltage. There is no change in drain current. So if there is change here, this guy is not changing. So which means the output current is infinite. So if it is infinite, very, very high, any change is not going to result into any difference in the drain current. So this is another important parameter, that it depicts a high output resistance. And in this region, we operate in the saturation region, we use it as an amplifier because the drain current is constant and it's determined just by the gate voltage or overdrive voltage, and it's independent of the drain to source current. So by using this in this range, we can simply use the relationship that we had for the saturation, half Kn prime W over L, or we can bring it together in Kn VGS minus VT. I'm going to start writing VTN because we're going to be looking at PMOS, and in that case we have to look at threshold voltage for N-type and P-type. So here is the power squared, and if we just write it in terms of V overdrive, then we'll just VOV square for that. So this is the operation of a transistor and its characteristics, where we are looking at the relation of the drain current with respect to drain voltage, the drain current with respect to drain to source voltage, and drain current with respect to gate voltage. So in both cases, we identify that in triode, it behaves as a parabolic, but then when it gets to saturation, then drain to source voltage loses control over it. The only thing that matters is then the gate voltage. Now, in the enhancement mode, there's another interesting thing, that if we keep VDS constant, then by changing VGS, we can change the drain current, right? So another way of looking at it, that if we keep drain voltage constant, our drain current is only changing with our gate voltage. So this is the same relationship which I just wrote. So again, this region and cutoff is used for on and off, and this is used for amplification. Now, for the saturation region operation, we said that the large signal equivalent circuit shows that when in saturation, the drain current is independent of the drain voltage, VDS. So any small change in the drain voltage, drain to source voltage, would cause no change in drain current, which would mean that if you look at the resistance into the drain of a saturated MOSFET, you will see infinite resistance. It's an ideal case, but in here we think that once the channel is pinched off, there's no increase in the drain to source voltage is going to affect the channel shape. But in reality, when drain to source voltage is increased beyond the overdrive voltage, it does affect the channel somewhat. Specifically, as the drain source voltage is increased, the additional voltage drop which happens at the drain side is because of this narrow depression region, which is because of drain being in the reverse bias. And this voltage drop accelerates the electrons that would get to the drain end of the channel and then sweep them across the depletion region into the drain. Now, this is a depletion layer effect, which is widening. And then this is then resulting into is a direct result of channel length being reduced. So then there is reduction of this channel from L by a factor delta L. So now we are going through a channel which is smaller than the actual physical length of the channel. So this phenomenon is called channel length modulation. And now since the ID is inversely proportional to channel length, so it's going to have effect on the drain current. So hence length reducing would mean drain current will increase with drain to source voltage. Now this effect is accounted for in the drain current expression by a factor lambda, which is shown here. Now this lambda is a device parameter which has the units of reciprocal volts. So 1 over V is the unit of this lambda guy. And it depends on how the device is fabricated and what is the channel length that's been chosen for a specific device. So the value of lambda is much larger for new devices because the length is very small. So lengths are becoming smaller and smaller, and there is much more effect of channel length now on drain current. So for a given process technology now, lambda is becoming more significant because the length is becoming smaller and smaller. How do we find or calculate this lambda? So there is a relationship or a graphical representation of the behavior of a MOSFET. So in this one, so we see that drain current gets into saturation. Now instead of showing a straight line like this, we are showing it like this. So hence we are incorporating the effect of length. So in this ID/VDS curve, if we extend the straight line of these ID/VD characteristics, we would hit the drain source at some value. This is called early voltage. VA is called early voltage. Early after the name of a scientist who identified this behavior. And this phenomena is common to bipolar junction transistor, other transistors as well. So what we see here is now the VDS is in minus side, and we have early voltage on with respect to that, but it's a positive voltage. So but what we mean here is ID is equal to 0 at VDS is equal to minus 1 over lambda. So we can then write down VA is equal to 1 over lambda, and this early voltage has direct dependence on the device parameter of a device, which has dimensions that are related to channel length through this lambda. This early voltage falls in the range of 5 volt per micrometer to 50 volt per micrometer. So it's a has significant effect, and this can directly result into helping us find the output resistance of a device. So now when we take the channel length into account, we can see that the output voltage has an effect on the drain current, so hence it is not finite resistance. So if I take my relationship of drain current and I plug in now the factor which is lambda. I guess I get Vtm squared 1 plus lambda ds. So from this one, for a small change in drain to source voltage, we can find a small change into the drain current. So now voltage change with respect to current change is the resistance. So hence the output resistance of the current source, which is when represents ID in saturation, is no more infinite, but it is the current divided by the voltage divided by current, just like for a ohmic relationship. So, but here I'm writing it reverse because we are seeing current change with respect to voltage change. And this is while we are keeping VGS as constant. So this is an important relationship because we are finding now the output resistance of a transistor. So taking derivative of this guy with respect to VDS, we can simplify and write it as R naught equals 1 over lambda ID, which is we have to play with this to do the differentiation, and we get there. Now lambda is 1 over lambda is A, so I can write it 1 over lambda is early current, early voltage, so I can write it like VA over ID. So in this case, we are taking the early voltage, so we are taking the lambda dependence out, so I can write ID prime as the drain current without channel length modulation taken into account. So hence this is something where we would take this out and the remaining would be then ID prime for us, just to telling us that there is no significant effect of the lambda when we are incorporating that effect through early voltage here. So hence the output resistance is inversely proportional to drain current, and the large signal model can be then modified and the output resistance incorporated, which takes care of the finite resistance at the output.